transformers. Uh, okay. Hi everyone. Today is the week 6 problem solving session for Bioreactor Design and Analysis. So let's start off with the first question. So the question is which among the following statement is are true for sterilization operations? So there are four options. The first is heat generated in a bioreactor is generally due to the heat of mixing and heat of metabolism. The second is sterilization and controlling reactor temperature are two of the most common heat transfer applications in bioreactor operation. The third option is in batch sterilization operations, the hold time can be minimized by taking into account the cell destruction during heating and cooling periods. The fourth option, in a continuous sterilization, the time of exposure to desired sterilization temperature is independent of the length of pipe in the holding session. So, in this, since there are four options given, either one or more than one can be true. So, what do you think the answer is? Just think about it. You're looking for statements which are true when with respect to sterilization operations. So let's see what the answer is. So the answer is all A, B, and C. So the only thing that was not right is in continuous sterilization, the time of exposure to the desired sterilization temperature is independent of the length of pipe in the holding session, and that is not true. So it is very much dependent on the length of the pipe in the holding session, and that is a factor that you consider when you are thinking about the time of exposure to whatever sterilization temperature that you're using. So let's move on to question number 2. So during sterilization, the operating temperature and time depends on the kinetics of inactivation of the cell. And the kinetics of inactivation in this case means how the system will behave, right? So is it true or is it false? Does the operating temperature and time depend on the kinetics of inactivation of the cell? And the answer is in this case is simple. It is true. Yes, the operating temperature and time depends on the uh, kinetics of inactivation of the cell, right? So in this case, um, depending on the kinetics of inactivation, you can have certain operating temperature and the time that is required for sterilization to take place, right? Because you would have noticed at certain temperature that cells, are reduced to a certain extent. Okay, so the match of the time and the temperature used will be a factor of the kinetics of inactivation. So let's move on to question number 3. So consider an enzymatic system which has immobilized, uh, which is immobilized in spherical beads following Michaelis-Menten kinetics. For the system, when internal diffusion limits the enzymatic reaction rate, the apparent maximum velocity and the Km deviate from their respective intrinsic value. So you might have to read this a little so that over again so that you understand what the question is. So in case you have an immobilized spherical bead enzymatic system, when there is the diffusion, the internal diffusion is limited. Is the Vmax and Km the actual Vmax or Km, or is it a deviation from their value that you would see in case they were not immobilized? So the answer is true, and the reasons I have been taught to you in class. So, when internal diffusion limits the enzymatic reaction rate, the rate constant and Vm and Km are not true to their intrinsic rate constant but apparent values. For you to obtain the true constant, the diffusion resistance should be eliminated. So for to do that, you have to use very small particle sizes. You have to have a high degree of turbulence around the particles so that the substrate gets to go into the particle, and a very high substrate concentration too. Okay, let's move on to question number 3. Sorry, question number 4. So which among the following is not true for continuous sterilization using steam injector? So the continuous there are three options in this. The option number one is the continuous stream injector injects steam directly into the unsterile broth. B is foaming may occur when continuous steam injector is used for sterilization. And C is direct contact of the medium with steam does not require allowance to be made for the dilution caused by the condensate. So which is not true? There is only one option, or there could be more also, depending. So the answer in this case is C. So if you think logically, the continuous steam injector does inject steam directly into the unsterile broth, and foaming does occur when steam is injected into sterilization. But direct contact of the medium with steam also requires allowances to be made for dilution caused by the condensate, because the steam is vaporized water, right? So that will add to the media that you're using, and that will cause dilution, right? So you have to make allowances for that. So the correct option is option C in this case. So let's move on to question number 5. So question number 5 is the kind where you have to determine the correctness of an assertion and a following reason. So the assertion in this case is, for any sterilization operation, relatively high temperature with short sterilization time is most preferred mode of sterilization. And the reason for this assertion that they're giving is that the mode of sterilization with high temperature and short sterilization time, it favors a rapid killing of vegetative cells and spores. Okay, and it causes minimal denaturation of nutrient components of the liquid broth. So what is correct? So either both A and R can be true, and R can be the reason for A. A and R can be true separately, but R is not the reason for A. A can be true, R can be false. A can be false, R can be true. Both A and R can also be false. So the correct answer in this case is A, option A. Both A and R are true, and R is the correct reason for the assertion A. Okay, so it is true that we like high temperature short sterilization time, and that is because it kills off vegetative cells and spores, and because it's a short temperature, you do it with minimal denaturation to the components present in the media. So this is question number 6. So this is a numerical problem, so let's read the question carefully. So a continuous well mixed bubble column is used for the conversion of tyrosine to dopa. Okay, 3 millimeter spherical beads are used to immobilize tyrosinase that catalyze the conversion of tyrosine to dopa. The Michaelis constant for the immobilized enzyme is 5.76 gram mole per meter cube, and 20 gram mole per meter cube of tyrosine is fed into the reactor with desired conversion to be about 97%. Okay, so you want at least 97% of tyrosine to be converted to dopa. The reaction is loaded with beads, and the density of the reaction is at with the beads is at 0.35 meter cube per meter cube, right? The entire enzyme is retained within the reactor. The intrinsic Vmax for the immobilized enzyme is 1.285 into 10 to the power minus gram mole per second per meter cube beads. The effective diffusivity of tyrosine in the beads is 6.9 into 10 to the power 10 meter cube per second, and the external mass transfer effects are negligible. Immobilization stabilizes the enzyme so that the deactivation is minimal over the operating period. Okay. So you have the what is given to you in this question is the reaction follows the first order kinetics, where the reaction rate is only dependent on one of the substrates, uh, the concentration of one of the substrates, and the Thiel modulus for spherical bead following the first order kinetics is given. In this case, it is this formula, and the relationship between generalized Thiel modulus and internal effectiveness factor for a spherical catalyst follows the first following the first order kinetics is given by this formula, right? So, what is the first question? So you have to determine the generalized CL modulus for this given spherical bead. So you know that the diameter is 3 millimeter. You have to convert it into meter. That is 3 into 10 to power minus 3 meter. The radius is given as 1.5 into 10 to power minus 3 meter. The Michaelis constant Km is given as 5.76 gram mole per meter cube. The intrinsic Vmax is given as 1.285 into 10 to power minus 2 gram moles per meter cube bead, and the effective diffusivity, that is dA, is 6.9 into 10 to the power minus 10 meter cube per second. Okay. So first you will have to find the reaction rate, which is given by Vmax by Km, and you know both Vmax by Km. 1.82 into 10 to the power minus 2 divided by 5.76 will give you 2.231 into 10 to the power minus 3 per second. Okay. So now the generalized seal modulus, according to the formula that they've given you here, is R by 3 and root of K1 by dA. So R is 1.5 into 10 to the power minus 3 divided by 3, and the root of K1 that you've just found here, 2.231 into 10 to the power minus 3 divided by Km, dA, which is given as 6.9 into 10 to the power minus 10. So the generalized seal modulus for the spherical bead you will find as 0.8991. Okay. Now you have to find the internal effectiveness factor. So from the formula given here, you know that internal effectiveness factor is a function of the generalized seal modulus, and you've just found the generalized seal modulus here, right? So adding, putting the Thiel modulus in this case, this is the sign for the Thiel modulus, right? That is what you get. 1 by 3 into Thiel modulus square in the this factor multiplied by 3 into Thiel modulus cot 3 into Thiel modulus minus 1. Okay. So in this case, if you're using a web calculator, you can just find out what the value of 3 into Thiel modulus is and find the uh, cot value, okay, and put it in the formula here. Or if you're using a scientific calculator, you can select the hyperbolic function and select tan. Okay, you will get the function of tan h, right? So now cot h x will be equal to 1 by tan h. So you can find the tan h value of x. In this case, it will be the uh, you know the Thiel modulus, right? And you take the inverse of that and you will get cottage of Thiel modulus. So what you find is 0.71, which is the internal effectiveness factor. Now, since they're telling you in the question that the external mass transfer effects are negligible, so you know that the external effectiveness factor can only be 1. Okay, so that the total effectiveness factor is at the highest because of the internal effectiveness factor, right? So bi- now you have to determine the dilution rate in terms of per second. Okay, so you know that the initial substrate is given as 20 gram per mole per meter cube. Okay, the conversion value, that is x, is 97% or 0.97. Okay, so conversion x is equal to initial substrate minus final substrate by initial substrate, right? So final substrate is given by initial substrate minus x into initial substrate. So you can take S naught as common and you get 1 minus x, and that is initial substrate, that is 20. and 1 minus 0.97. So you get 0.6. So the final concentration of the substrate is 0.6, right? And the total effectiveness, is multiplication, the product of internal effectiveness and external effectiveness, that is 0.71 into 1, right? So the actual reaction rate is given by, the formula for reaction rate into the total uh, effectiveness factor, right? So you know the total effectiveness factor, you know Vmax, you have found the final substrate, you know Km, again you know the final substrate. So this is 8.607 to 10 to the power minus 4 gram mole per second per meter cube is your actual reaction rate. And at the steady state of transfer, the actual reaction rate will be equal to the consumption of the substrate at the rate of consumption of the substrate, which will be equal to the input of the substrate minus the output of the substrate, right? So that is equal to the dilution factor into the initial substrate minus the final substrate. Okay. So you have to find the dilution rate from this in this case, because that is what the question is asking. So you have 8.607 10 to the power minus 4 gram mole per second per meter cube divided by initial substrate minus final substrate. Initial substrate is 20 and final substrate is 0.6. So you get the dilution rate as 4.4366 into 10 to the power minus 4 per second. Okay. Now you have to determine the reactor volume in terms of meter cube needed to treat 25 meter cube of tyrosine solution per day. So you know that the volume is equal to the flow rate by the dilution rate. So it is saying 25 meter cube uh, and per day, right? So you have to convert that day into seconds, right? So that is one day is equal to 24 hours into each hour is equal to 3600 seconds, right? So that is the conversion factor divided by the dilution factor, which is 4.4366 into 10 to the power minus 5 per second. Okay. So you get the reactor volume needed to treat 25 meter cube of tyrosine solution per day to be 6.522 meter cube. Right? So that is all for today. I hope you understood this. Thank you for listening.